So, finally, to summarize, the state space representation of a SISO LTI causal dynamic system is going to take this form. Okay. In general, it is going to be x dot t equals axt plus but, okay. Y of t is going to be equal to c dot xt plus dut. Okay, that is the state space representation of a SISO LTI causal dynamic system. Okay. So, the first equation is what is called as a state equation. Okay. The second equation is what is called as an output equation. So, we will see that typically when it is applied to practical problems, like when you measure y, some people will call it as measurement equation in estimation theory and so on. Okay. The output equation is also called measurement equation. Okay. So, yeah, we will use the general terms. Okay. So, this is the state equation, output equation. So, please remember once again, the output state equation is a vector ODE, right, but it is a first order ODE. Okay. And the output equation essentially relates the output to the state variables. So, you can see what has happened here, right. So, in the transfer function representation of the mass spring damper system, what did we do? We directly took the Laplace of the output to the Laplace of the input as 1 by ms squared plus Cs plus k, right. You give me any input, I can directly calculate the output. Here what has happened is that, yes, we are given an input. What we do is that we first solve for the state variables, which in a certain sense characterize the internal dynamics of the system, okay, and then get the output from the state variables. Okay. So, it is a two-step process, okay, as to what we are doing. So, for that reason, like the transfer function representation is also what is called as an external representation of the system, okay, because it directly relates the input and the output. The state space representation is what is called as the internal representation of the system, okay, or represents what is called as the internal dynamics of the system, okay, because we go through the state vector. Okay. So, that is what we are doing in the state space representation.
So, what is the significance of
State space, okay, because you are going to have a vector as a state variable, right, state vector, right. So, you are essentially going to the space of state variables, right, it is a vector space. Okay. So, that is why it is called a state space representation. Okay. It is a space of state variables. Okay. Yeah. So, that characterizes the system. Okay. So, and typically the set A, B, C, D is what is called as a realization of a system. Okay. So, that is a terminology which we will encounter, okay, that is what is called as a realization of a system, okay, fine. So, now similarly the state space representation of a MIMO LTI causal dynamic system is going to be the following. Okay. So, what happens in the case of a multiple input, multiple output dynamic system? What is going to happen is that x dot t is going to be equal to axt plus capital B u t. Okay, now u is a vector. Okay, the matrix, you will still have n state variables, n being the order of the system. Okay, but the change is the second term, which is b u t, b will become a matrix. Okay, because u is a vector. And similarly, the output equation, since y is a vector, we will have it as c x of t plus d u of t. Okay, so that's the change which would happen. I'm sorry, what is that? No, we don't have, but I'm just introducing it to you, right? So yeah, so essentially, let us say, consider, let's say m inputs. Okay, or let me use a different character. Let's say p inputs and q outputs. Okay, of course p q greater than 1, right, for a memo system. Okay, so now what do you think will be the size of each of these matrices? The what to say, the state matrix A is still the state matrix, that will be n by n. Okay, that is not going to change, right? Now B is the input matrix, right? What will be the size of the input matrix? So B is now called as an input matrix. Okay. Okay. Previously, small b was called as an input vector. Okay. Now it's called input matrix. What do you think should be the size? It's going to be equal to n cross p, right? Because you are multiplying a vector of dimension p, right? U is a vector of dimension p, right? Because there are p inputs, right? So then you must have p columns in B, and the product gives you a vector x dot has n column, n is of dimension n, right? So the number of rows in B should be n. So that's why we get the size of B to be n by p, right? And then like C, the matrix C, what is it going to be? We call it as the output matrix. Okay, what would be the dimension? It's going to be q by n, right? So that's what we are going to get for C. And what about the size of D? D is what is called as the direct transmission matrix. What is the size of D now? It's going to be q by b, q by p, right? Because please note that D is multiplying U, right? U's dimension is p, so it must have p columns, and it is mapped to Y, which is whose dimension is q. So D must have q rows, right? So then in the memo domain, right, the matrices A, B, C, D form what is called as a realization. Okay, here we don't have the issue of notation of C and C transpose. Okay, so the matrix is C, that's it. Okay, so only in the SISO case, depending on how you wrote, depending on which school of thought you followed for notations, you write either as C dot X or C transpose X. Okay, here it's just Cx, that's it. Okay, no problem. But anyway, I just wanted to introduce it to you so that like you are aware of what happens in the case of a memo system, right? Now, to summarize, so if you look at our class of systems, right, LTI, causal, dynamic systems, right, once we get the model in the form of let's say ODEs, linear ODEs with constant coefficients, right, we do two things, right? So let's say if we apply the Laplace transform, with 0 initial conditions, okay, what we get is what is called as a transfer function, right? Representation. Okay. So, similarly, if we just rewrite as n first order ODEs, okay, we get what is called as the state space representation, okay, just from a bird's eye viewpoint, right. So, that is what we have, right, if we just rewrite in terms of first order ODEs, right. Now, this transfer function representation, because it just directly relates the input and output, it is also called as the external representation, okay, of the system or the plant, since we directly take the Laplace of the output and relate it to the Laplace of the input, right, through the transfer function. So, here since we first go through the state vector and then to the output, right, we call this as a internal representation. Okay. So, the second important point which we need to realize from our perspective is that we do analysis in the complex domain, right, as far as the transfer function representation is concerned, right, because S is a complex variable, right. So, as far as state space representation is concerned, the analysis is done in the time domain, okay. So, we essentially stay in the in a domain of real numbers, right, and then do the analysis, okay. So, of course, I can write many other identifiers, but as of now, you know, like these distinguishing characteristics are fine with us, okay. So, that is something which we need to remember, okay, regarding the transfer function and the state space representation. As I told you, this course is about transfer function representation, right. And we will also see that when we go to state space representation, you can analyze both free response and forced response, okay. We do not make the assumption that the initial condition needs to be 0, and that gives rise to the fact notion of stability called stability of an equilibrium and so on, okay. So, which we will not go into here, but we will look at those, you know, when you come to let us say an advanced course in controls that deals with the state space representation, right, okay. So, this is essentially something which I want to introduce. Now, let me essentially show you what is the equivalence between the transfer function and state space representation. Then I will leave you with an exercise to do, right. So, so essentially, are there any questions till now? External representation, because in the transfer function representation, what do we do? Let us say I take the transfer function P of s, you give me an input u, I just multiply P of s with u of s, and then I get y of s, right. I directly map the input to the output, okay. So, in a certain sense, I am looking at the system as a big box, as a single entity. I give the input and I get the output, right. But in the state space, what happens is that we essentially give an input u of t that essentially first gives me x of t, because you integrate the state equation to get x of t, then you use the output equation to get y of t, right. Oops, what happened? Okay. So, that is in turn used to essentially get y of t. So, what people will say is that, look, you know, like you internally you have a state vector, this is just a visualization, and the input and the output are related through the state vector, which characterizes the internal dynamics of the system, okay. So, that is why it is called as the internal representation, okay, of a system. That is the terminology. I'm sorry, what is it?
We can also say that P of S characterizes the internal.
Absolutely. It is just like, it's just a representation. Okay, whether we are essentially, P of S has information about the dynamics of the system, obviously. Just like the state vector will have information about the dynamics of the system, P of S also has, information. Okay, and of course, one important point which plays a critical role later is that the transfer function representation for a given system, once you fix the system on the governing equation, it's unique, but the state space representation is non-unique. Okay, so in fact that's an important attribute, because if I give the mass spring damper system, all of us in this room will get the same transfer function, 1 by ms squared plus cs plus k, but state space representation, depending on what state variables we choose, right, the representation will be different, but they will be equivalent to each other. Finally, you give the same input, the state variables may be different, but the output will be the same. Okay, that's assumed, right, but you can have a non-unique state space representation. Okay, so that's important. Okay, so let's just consider the SSO LTI causal and dynamic systems. Okay, so let's restrict ourselves to SSO, this one, right. So we know that the state space representation is going to be x dot t equals axt plus but, and the output equation is going to be c dot xt. Once as I told you, you can also write c transpose x. Okay, absolutely no problem. I am just writing c dot x. Okay, so just a notation, right? Okay, so that's what. Now this is the state space representation. I want to essentially figure out what is the transfer function of the system, right? So although it's a vector ODE, I can still take the Laplace transform, right, because it's a linear ODE, right. So take the Laplace transform. Okay, of this equation. So what do we get for x dot? It's going to be s times x of s minus small x0. That's going to be equal to a times capital X of s plus b u of s, right? That's what we get, isn't it? Okay, so let the initial conditions be 0. That is, we take x0 to be equal to 0, right? So what does this imply? S times x of s is going to be equal to a times x of s plus b u of s, right? So that's what I'm going to have. So x of s is common. If I take both terms to the left hand side, what will multiply x of s? I will have si minus a. See, I can write s minus a, okay, because a is a matrix, so I need to write si minus a, right? I being the identity matrix of dimension n, right? So that's going to be equal to b times u of s, and assuming that the inverse exists, so x of s is going to be equal to si minus a inverse b u of s. Okay. That's going to be capital X of s. Okay, I'll just be done in a couple of minutes. Okay, so similarly, take the Laplace transform of the output equation. So if you take the Laplace transform of the output equation, what are we going to get? We are going to get y of s is going to be equal to c dot x of s plus d times u of s. So this will give me c dot x of s is going to be c dot si minus a inverse b u of s plus d times u of s. So this would imply y of s is equal to c dot Si minus A inverse B plus D times U of S. Correct? So, I am just doing simple algebra, that is it. So, now what is the term within the square bracket? P of S, the Plant transfer function, right? See, what is the definition of the Plant transfer function? It is the ratio of the Laplace of the output to the Laplace of the input when all initial conditions are 0. That is what we did, right? So, this implies that the Plant transfer function is going to be equal to, for the SISO general class of SISO LTI causal systems, the Plant transfer function is related to the state space representation through this formula, okay, C dot Si minus A inverse B plus D. So, what is the sequence of operation here? So, you calculate Si minus A, you take the inverse, multiply that resultant matrix with B, you will get a vector, then take C dot that vector, right, you will get a scalar function of S, right. So, that is the relationship, okay, between the transfer function and state space. So, as homework, what I am going to do is that I am going to ask you to check this equation or relationship for the mass spring damper system. Okay, we already know the transfer function and ABCD for the mass spring damper system, right? Correct? So, please check it for the mass spring damper system, okay, and then another exercise, calculate the poles of the transfer function and the eigenvalues of the state matrix, okay, and comment. Okay, please do these two problems and then like we will meet in tomorrow's class and continue with the discussion, right.